In addition, I should probably note that I originally wrote this presentation for Code Camp, which is where a lot of software developers get together and review stuff. So there's a lot of jokes and references that are applicable to software developers. So if you don't get all the jokes, don't worry, they're not that funny anyways. So I've been doing Agile software development in one shape or form or another for about 14 years now. I got my start back in 1999, but back then we didn't know that what we were doing was called Agile software. In fact, the term Agile was the point based on what we're doing is what you had to do with small software. But I knew it was different from traditional software development. And in fact, I actually thought it was inferior in some ways from traditional software development. It seemed like we simply didn't have enough time, money, or resources in order to create software the right way. So it just felt like we were cutting corners. But luckily for us, this way of developing software worked out extremely well. And lucky for the industry as a whole, this Agile thing really did well. And fast forward about a decade and a half, and essentially something like 80% of all software projects are now being done using Agile, or at least they're trying to do Agile. And over the years, I've learned a lot about Agile from having good mentors, from industry experts, reading books, and practicing Agile. In addition, I've learned a lot about why Agile is successful. But interestingly, this information didn't really come from the Agile experts. It came from the things I was studying in college, computer science, economics, and psychology. I think it's important to understand why Agile is successful, because when you build Agile software, it's inevitable that you'll run into a problem, something you've never seen before, and you'll have to make a decision. And you want that decision to fall in accord with the Agile spirit, the spirit of Agile, so that you get the benefits of Agile. But to make a sound decision requires a different advantages. Why is Agile successful? Why is it working? And that leads me to the purpose of my presentation today. My purpose today is to attempt to explain why the Agile practices are so successful by insight from multiple disciplines, including economics, psychology, and various fields of science, things of interest to all scientists. There's a lot of ideas I'd like to talk about, but we're going to focus mostly on like the 7 most important ideas from this list. And these are ideas that are not typically covered in your regular Agile presentations, either because they're not well understood, they're ideas that require non-trivial explanations, or because they require like a synthesis of ideas. In addition, I think it's also important to let you know what we're not going to cover today. Because if you're not going to get value from this presentation, there's no sense spending the next hour 15 minutes listening to me talk. So the things we're not going to be covering are a basic introduction to Agile. There's plenty of sources you can go for this information. In fact, I give intro to Agile presentations every now and then. We're also not going to be covering basic or obvious explanations for the success of Agile. There's other sources you can go. And on the other end of the spectrum, we're not going to be providing like a comprehensive theory of the success of Agile. We're just going to pick and choose some of the high notes that I think you guys will find most interesting. And I will really quickly provide just a brief overview of Agile, just to make sure everyone's on the same page for anyone that just to essentially get So before we get into the main content of the presentation, just a quick bit of information about me. I'm an independent software consultant with about 14 years of professional experience building large-scale stuff. I got my start in the GIS industry, did stuff in energy data management, then worked on a global data management system for seafield operations. And I'm currently working on intelligent financial system software. And on my free time, I'm building what I'm calling an open source casual data explorer. It's an interactive data visualization. So if this is something of interest to you, come talk to me afterwards. I'd love to chat about it. I have double degrees in computer science and philosophy with a minor in economics from Iowa State University. My focus was on artificial intelligence and machine learning, in addition to associate's degrees in management information systems and business administration. I'm also a certified Scrum Master, but I should probably note that I'm not really interested in being a Scrum Master. I'm a software developer, so my interests are coaching and mentoring software developers on new practices, like test-driven development and continuous improvement. Okay, so we'll do that quick review of Agile first, and then we'll move into the main presentation, which is the first topic is the world after midnight, then Inversion of Constraints, prioritizing value, embracing change, self-organization, efficient communication, and finally we'll end with feedback. And we'll probably have to hold questions until the end because we've got a large room and we've got kind of a short time period to fit everything in. And I have a tendency to get kind of derailed and go off on wild tangents when we ask me questions. So, all right, first, brief review of Agile, just to make sure we're on the same page. So, what is Agile? Well, it started with the Agile Manifesto back in 2005, which summarized 4 value propositions and 12 principles that were found common amongst a set of software methodologies and common. What Agile is not, however, is an individual software methodology in and of itself. It's essentially like an umbrella term that covers a lot of software development methodologies. In addition, it's not like a magic silver bullet that solves all your software bugs. Software development is complicated. It's always going to be complicated. There's things that we can do to make it easier, but ultimately, there's nothing that just magically going to solve complexity problems. The Agile values are individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, and responding to change over quality. And it's not to say that Agile doesn't blame like individuals and processes and tools, but rather we give the choice to choose between individuals and interactions versus processes and tools. Agile would typically choose the individuals and interactions and only apply as much processes and tools as necessary to do the job. And I'll just real quickly skim through the 12 principles of Agile, since I assume most of you have already seen this. Is this better? First is continuous delivery of value, then embracing changing requirements, frequent deployment, customer collaboration, motivated individuals, face-to-face conversation, working software as a measure of success, sustainable development, technical excellence, simplicity, self-organization, and continuous improvement. And as I mentioned before, Agile is not a methodology in and of itself. It's kind of an umbrella term that captures a series of software development methodologies. So we have Scrum, XP, Kanban, and there's many more too. And if you're interested in seeing a distribution of the software development methodologies, or Agile methodologies in use, this is the latest survey I saw from version 1 in 2012. So over here we have Scrum, with about half of all software projects being done in Scrum. Then we've got a Scrum XP hybrid here with about 11%, custom hybrid at 9%, Scrum Bond, which is a combination of Scrum and Kanban at 7%, then just Kanban itself at 4%. Then there's 4% of people who don't even know what they're doing. XP, FTD, and there's others too. And finally, to conclude our quick review of Agile, let's just get this question out of the way. Is Agile actually more successful than traditional software development? Well, most of the research I've seen, at least recently, all shows roughly the same kind of conclusion. So we have Agile projects here. This is the Standish Group's Chaos Report 2012 data. We have Agile projects here with approximately 42% successful projects, and this is based upon standard project metrics. We have 49% were challenged and 9% failed. In the Waterfall world, we only had 14% that were considered successful, 57% considered challenged, and 29% that were considered failed. And so I think this settles the debate once and for all. Pie charts with really ugly colors are like a terrible way to represent quantitative measures. See, that was one of the jokes for the data visualization, guys. Okay, so the first idea we need to talk about here is something referred to as the world.
Was that the last time?
Quick show of hands. Has anyone heard of this concept before? You were at my last presentation. All right, we're all going to learn something new except for voice. So, back in 2012, a British professor by the name of Eddie O'Brien gave a TED Talk that he titled The World After Midnight. And in his presentation, he discussed a realization that he had several years ago. He said, about 15 years ago, all the rules about how to run a business, organization, or government successfully were changed or deleted, and a completely new set of rules has been operating ever since. Which means that we keep acting rationally in response to a world we recognize and understand, but which no longer exists. He tried to get this idea across by drawing this diagram, which outside of the context of him explaining it as he's drawing it, isn't very clear. Okay. So I'm going to try cleaning it up a bit. So on the x-axis we have time, starting in the past and leading to now. And then on the y-axis we have two curves. First is this rate of change curve, rate of learning curve in blue. And this is the rate at which human beings can learn. And it's been slowly increasing over time with technology and stuff. And then second, we have the rate of change of technology, society, and markets. And as you can see, this rate is increasing faster than the rate of learning, and it overtakes it here in the middle somewhere. As Professor Obeng assumes, about 15 years ago, something happened in our society that caused this rate of change curve to ramp up quite dramatically. And he believes it has something to do with the internet coming into the mainstream. Well, eventually, this curve, rate of change curve, overtook the rate of learning curve, and something fundamentally different happened. Essentially, the world we live in today says is fundamentally different from the world of 15 years ago. And at the point of intersection between these two lines, he drew this dashed line here, which he metaphorically referred to as midnight. And The metaphor makes a lot more sense if we tell the story, but for our purposes, we just need to know that this is big. So we have the old world here on the left, and we have the new world on the right. And in the old world, we have this rate of change is slower than the rate of learning. So we can sit back, we can look at a problem, we can design a solution, think about it for a while, build a product over a couple of years, and then we get our product out there, and eventually we have several years to capitalize on it. In this new world, however, the rate at which the world is changing is faster than the rate at which we can learn how to adapt to these changes. So we can't just sit back, we don't have years of time to capitalize on things, and we don't have years to build a product. We've got to build something fast, get it out there, and start capitalizing on it right away, and then roll with the punches continuously as the world is changing around it. In essence, the old world is characterized by the inertial forces of bureaucracy, process, and tradition, and the new world is characterized by the dynamic forces of communication, collaboration, and learning. And this isn't a trivial change in the way the world works, the old world works versus the new world works. In fact, it's fundamentally different in terms of how you interact with this world and how you operate and succeed within it. The dynamics are totally different. In an attempt to convey how radically different these two worlds were, Professor Oben used a metaphor from an area of physics called fluid dynamics. So imagine for me, if you will, that you've got this tube of flowing water, and you inject a bit of red dye into the water. At low velocities, we have something referred to as laminar flow, where the water moves in relatively fluid parallel lines with minimal disruption to the layers. If we increase the velocity of the water, we end up with these little eddies or ripples in the water that disrupt the parallel and smooth flow. And then eventually at a tipping point, which happens relatively fast, we end up with turbulent flow, which is this chaotic and kind of random system. It looks chaotic and random to us. In laminar flow, the physics are simple and deterministic. And in chaotic flow, in turbulent flow, the dynamics are chaotic and stochastic and non-deterministic. So we have two entirely different worlds operating here, and two entirely different sets of physics that we use in law. The world, similarly, the world that we currently live in went through a similar type of change. And most people are still operating as if they're living in this old world yet. When in fact, this new world is currently what's around them, and they haven't updated their rules or their models or the way that they approach the world in order to understand how to succeed with it. And if you're questioning whether this is a real phenomenon or not, this is something I found that I think might help to clarify that something really is going on. So on the x-axis, we have time starting with the 1950s and late 2000s. And on the y-axis, we have something called influence index of business facts. And as you can see, somewhere here in the 1980s, something happened in the business world that has caused the explosion of new business facts. And it really does look like something has changed overnight. And now the world is actually like scrambling and trying to catch up and figuring out how to respond to it. And whether this is true or not, I mean, be healthily skeptical. But I think for the most part, it seems like something really different. Okay, so why is this important and what does it have to do with Agile? Well, if the world we live in really has changed, like Professor Oben says or believes it has, then we need to adapt to this new set of physics. And if markets are changing rapidly, we need faster time to market. And if requirements are changing rapidly, we need better ways to respond to change. And if there's a higher degree of uncertainty in the marketplace or in the new world, we need new ways to mitigate this risk by doing things like continuous and rapid feedback, validated learning, and smart field. In a nutshell, Agile is very well suited to operate the physics of this world. And this is essentially the main point of my presentation. Everything else will be an attempt to explain why I think this is the case. The next idea I'd like to talk about is inverted constraints. Okay. Imagine for me, if you will, that you're a software project manager, and you've got these 4 levers in front of you. First, you've got a lever of scope, which is the amount of stuff you have to get done. These are the requirements. Then you've got resources, which is the people and the tools that you have to get this stuff done. You've got schedule, which is the amount of time you have to get all the stuff done. And you've got quality, which is how good the stuff is that you create. So your goal as a software project manager, then, is to adjust these 4 levers in a way that creates working software. Working software that maximizes value and minimizes cost. However, the real world is not this ideal because of these things referred to as constraints, which are restrictions on a degree of freedom, like the wall between you and the baseball you're trying to catch. And they prevent the system from achieving its goal, like our goal of creating working software. So each of those 4 levers has constraints applied to them, things like time, money, and capital, that make software development less effective. So if the world was simple, we could solve all these problems with mathematics. Things, optimal allocation of scarce resources through constraints, could be done with these mathematical models in your program. And I don't want to overly map you guys out. This is just to show you that there are ways to solve these problems if the world was simple. So imagine we just got 2 of these levers. We're just going to worry about 2 of the 4 levers. We've got one lever here on the x-axis that we move forward and backwards, and another lever on the y-axis that we can move up and down. And then we've got this solid blue and solid green line, which are the constraints. These are the things pushing back against our levers. And you can see that we can exchange things in varying degrees for the most part. Then we've got these dashed lines here, which represent either ISO value lines, or they're called ISO value lines, or also ISO cost lines, depending upon whether you're trying to minimize your cost or maximize your value. And these dashed lines increase as you move out. Then we've got this shaded region here. This is the feasible region. This is all possible combinations of positions where we can set those 2 levers. And then this point in the center here, this is essentially our optimal solution. So this is the point where we set both levers in order to maximize value or minimize cost. Unfortunately, the real world isn't so simple, and we've got 4 levers to deal with, so this problem becomes more complicated. And those of you that have taken like advanced calculus or economics know that we've got mathematical ways to solve these problems as well too, like the methods of Cronner's multipliers. But unfortunately, the real world is still not this simple. It's actually significantly more complicated. We've not only got a 4-dimensional problem, but it's also non-linear. It's got local minimum and maximum, and it's constantly changing too because of things like people. So ultimately, this way of solving problems using mathematics, it's just way too much. These problems are too difficult to solve using math. So we need to simplify things. So let's just look at 3 of the 4 constraints right now: scope, resources, and schedule. So in the waterfall world, or in waterfall projects, we fix scope and we estimate resources and schedule. So by fixing scope, we're saying we've got all this stuff to do. These are our requirements. By estimating resources and schedule, we're saying that, well, given all the stuff we have to do, we estimate that we can get it all done with 10 developers in 1 year, or we can get it done in half the time with twice the developers, or get it done, in 2 years with, half the developers. And this is typically how project management operates, so where the models that people use when they're trying to build software in the traditional way. Unfortunately, many project managers attempt to fix both scope and schedule. And so we've got all the stuff that we need to do, but we also have to get it done in this much time. And when someone does this, the project will fall, potentially fall behind. So they add more developers or throw more money at it. And this inevitably fails for reasons I mentioned in a bit. Even more unfortunate is that some ill-fated project managers attempt to fix all 3 of these constraints. So we've got 100 features we've got to do. We've got 6 months to do them all in, and we've only got 3 developers. So we're just going to have to get everything done. And when this happens, quality, which is the 4th hidden variable here, just goes out the window. And technical debt starts to accumulate because we've sacrificed quality. And once we sacrifice quality, this technical debt will accumulate, accrue interest, and will eventually drag the project into just completely stall. So we really have to protect quality. Quick show of hands, who's been on a project or something like this? I wish you guys could see how many hands are being raised. In Agile, however, we revert this, what's called the iron triangle project management, into something called the elastic triangle. They call it that because it's significant, flexible, and responsive to change. So rather than fixing scope and estimating resources and schedule, we fix resources and schedule and we estimate the scope. So by fixing resources, what we're saying is we're going to limit team size to 7 plus or minus 2 people, or 6 plus or minus 1, depending on who you're talking to, with preference for smaller teams. And by fixing resources, we're limiting the size of the teams that, by fixing schedule, we're saying that we're going to release software every 2 to 4 weeks. So that's just a given. There's always going to be a release of the software or potentially shipping the software every 2 to 4 weeks. And then we estimate scope. So given we've got this team of 7 plus or minus 2 people, and given that we are less than 7 plus or minus 2 people, and given that we've got this schedule of every 2 to 4 weeks, we assume that we can get, this much stuff done, or we'll get a little more done or a little less, but, it doesn't really matter. We're eventually good. These things kind of average out in the end. And this inversion of constraints has a fundamentally profound effect on the way software projects are managed. It avoids the mythical man, which is the diminishing marginal return you have by adding additional software developers to a project. Because you can't just double the amount of developers and expect the amount of time that the project takes to be cut in half. In addition, it prevents the inevitable slipping of deadlines which occur on many projects, software projects, because we always have potentially shippable software for 2 to 4 weeks. And moreover, it prevents the negative effects of scope creep by making scope variable in the first place. So if you need more features, that's fine. We can add more features, but you just have to anticipate that we'll take more sprints in the middle of it to get it done. And finally, it protects quality, because having variable scope gives us a bit of wiggle room, so that when developers realize that the quality is being sacrificed, they can push back a bit. And that's necessary in order to ensure that quality is maintained. This is metaphorically equivalent to like having an automobile production line that allows line workers to stop production when they see a quality defect that warrants halting production. And this is important because if we sacrifice quality, we're going to increase that technical debt. And the technical debt will accumulate and accrue interest and eventually bring the project to a halt. So we need to maintain this quality. And by maintaining high levels of quality, however, we can sustain our development velocity indefinitely over long periods of time. Essentially, if you want to go fast, like Ricky Bottom here, you've got to have quality. That was funny. My girlfriend laughed out loud. Thank you. Maybe my joke's this way. So, quality should be non-negotiable in software projects. Once you compromise the quality, your velocity is going to pay the cost in the long term. And it's acceptable to create short-term debt, but it's not acceptable to create long-term or reckless debt. The third idea we're going to talk about is prioritizing value. How's this going? Is everybody keeping up? Is it good? So, in order to discuss this idea, we're going to have a quick lesson in economics. So, quick show of hands, how many of you have had at least one class in economics? Oh, wow. I've been good company. That's awesome. All right. The first idea we're going to talk about is return on investment. The second idea is the Pareto principle. And the third idea is opportunity cost. So, first, return on investment. The return on investment, or ROI, of something is the value that you're getting from something minus the cost you put into it, all divided by the cost. So essentially, if you have a high return on investment, you've got lots of value out of your investment. If you have a low return on investment, you get some value, but not a whole lot. If you have negative return on investment, you've essentially lost value. So over the life of like an investment, a business, or a project, initially the return on investment is low when you're putting a lot of effort into it, but not putting a lot out of it. And eventually the return on investment will increase. And if you have a successful business, it'll eventually break even and you'll be in a profit area here. And then at the top, you'll eventually maximize your return on investment. And then, sales taper off relative to the fixed cost of running the business. Things like eventually go back down again. So in the software world, each feature also has a return on investment as well. So for any given feature, there's a cost to develop the feature and the value that that feature is providing. Our goal then, if we sum up all of the feature return on investment, we've got the full return on investment for the project. Our goal as a software project managers or a software businesses is to maximize this return on investment of the project as a whole. The second idea we need to talk about is the Pareto principle, which is commonly referred to as the 80-20 rule in popular literature. So the 80-20 rule states that in some systems modeled by power law functions, 80% of the effects are derived from 20% of the causes. Or in other words, 80% of the inputs are derived from 20% of the outputs. So if we look at the power law function here, we can see these 20% of the outputs, which are producing 80% of the results, or outputs. And we can see 80% of the inputs that are producing 20% of the outputs. This graphic might clear it up a bit more here, too. So the 80-20 rule captures this principle that in some systems, or that some systems are not balanced between their inputs and outputs. And in economics, this leads to diminishing marginal returns. So for each additional unit of effort we invest in something, we get less and less effort out over the margin. There are many systems that exhibit these power law functions in their day-to-day lives. In fact, they're like all over the place. One of these systems is actually software feature usage. So if we're building software using traditional software development, the empirical evidence that we've seen shows that approximately 7% of features are essentially always used and 13% are used often. If you sum this up, this ends up being 20% of features that are used about 80% of the time. The remainder of the features, sometimes used, rarely used, and never used, essentially sums to 80% as well. And this is the 80% of features that are being used approximately 20% of the time. So when you think about traditional software, you need to think about your features as 20% of them are high-value features, and 80% of them are low-value features. The third concept we need to talk about is opportunity cost. So economists look at cost differently than accountants. In fact, economists look at cost entirely differently than almost everybody. So in economics, the cost of something is not just what you paid for it, but what you also gave up by committing to one option rather than all the other options that you could have chosen. So consider hypothetically you make $50 an hour, and you usually take an hour-long lunch. And so your buddy Joe is like, hey, if you come over to my place, I'll make you a free lunch. And you're like, oh, free lunch? That sounds like an awesome idea. But it's going to take you an extra hour to get to his place. So if you go to Joe's place, you have your free lunch. How much did this lunch cost you? So the lunch itself was free, but essentially you've incurred $50 in opportunity cost because you've given up the option of spending 1 hour at work instead to drive to Joe's place, where you could have paid $50 in that time. And that's how we have to frame our decisions differently when we think in terms of economics or think like economists. So opportunity cost is the cost of foregone alternative options. And this view of cost considers both the explicit cost of things, the lunch was free, and the implicit cost of things. Essentially that you could have gotten $50 if you would have done something else with your time. So when making economic decisions or with an economics framework, when we make decisions, we make them in terms of cost-benefit analysis that we're taking both the implicit and the explicit costs into. And I think this cartoon really sums up how economists think about the world differently and why we probably don't have too many friends named Joe that offers free lunch. So why is this important and what does it have to do with Agile? Well, many Agile practices use this idea of a product backlog, which is a list of features that we order by business value, or the value that they'll provide when we release them to the business. We put the highest value features on top and the lowest value features on the bottom. And then we work on the features from the top on down, creating the features with the highest value first and working our way on down. And then we deliver the features in that order as well too. Ideally, we should really be prioritizing by the actual return on investment, so taking both the value that some features providing minus the cost. But in general, using the heuristic of highest business value is usually good enough in most cases. So you don't have to compute the actual performance or something. So if we have this backlog of features, which is prioritized by business value, and we're creating and delivering features according to business value, then essentially we're maximizing the return on investment for every feature that we create. And this is because each feature that we're creating is essentially the highest value feature that we could be creating relative to all of the other features that we create. This is also going to follow the 80-20 rule because we're going to build the 20% of features that provide 80% of the value first before we get to the 80% of features that only provide 20% of the value. In addition, this way of building software also recognizes opportunity cost. So it recognizes that if we were to spend today working on feature number 99, rather than working on feature 1 up here, we've essentially lost all of that opportunity cost that feature number 1 was providing. So I think in general, this way of building software, the economics behind it are relatively solid, at least according to everything that they taught me. So all of this produces a significantly different value over curve, value over time curve for Agile versus Waterfall projects. So, although this graphic is one of those like fluffy graphics because there's not any real data points behind it, I think it still captures the idea well. So, essentially on the x-axis we have time across the project, and on the y-axis we have the value that the project is giving us. In Waterfall, we don't see the value until late in the game because we have to release the software, which we release late relative to Agile, and we start seeing the value of the software coming in here. Whereas in the Agile world, we're releasing software really right off the bat, early and often, and we're capturing that value immediately. So we're accumulating value over the life of the project while we're developing the project itself. Okay, fourth idea I'd like to talk about is embracing change. Sorry, I have to take drinks of tea in between, otherwise I'll start talking really fast. So, Waterfall operates under the assumption that things will go according to a plan. So when the project begins, the project manager has in his mind that we'll start the project over here, and we'll march along diligently until we reach the finish line over here. But the reality of most plans doesn't look like this. It looks more like this. So essentially we start the project, we march along here a little bit, realize our original assumptions were incorrect, we got to back up a little bit, come up with some new requirements. We move further forward again, and then we realize that the technology we based our design on is obsolete or won't work for some reason, so we got to back up some more here. And then we move along here, and oops, the project manager quit, so we're all the way back here again. And if you're lucky enough to make it to the finish line, which most of us won't, because by the time you get about here, you're already double over, what you expected to spend or time-wise or money-wise on the project, and you most likely missed the market opportunity. It's already gone. So if you do make it to this finish line, you might also notice that the finish line wasn't up here like you expected. It's actually down here now. And the reason why is because the markets are changing, people's opinions about, or consumers' opinions about products are changing, and society is changing around you as well, and technology. So Waterfall operates under a few key assumptions. First, Waterfall assumes that users actually know what they want. How many of you have users that actually know what they want? Not a single hand. Not a single hand. I was hoping somebody would raise their hand, because if you do have users that actually know what they want, like, that's a company I want to work with. Because Waterfall also assumes that the markets will not change during development. In addition, that there's nothing new or unknown in the project, that technology is stable and mature, and that all of the pieces will fit together. If these assumptions were correct, then Waterfall would work extremely well with the way it builds software. However, the reality for most projects is that requirements are not stable. They're continuously changing over the development of the project, and requirements are just assumptions. So really think about this. Requirements are just assumptions. So when someone creates a software requirement, what they're really saying is that I assume that a user is going to derive value from this feature. It's not actually that they will derive value from it. It's essentially just an assumption until we validate it. So essentially, requirements are just assumptions. And speaking of things not going according to a plan, let's talk about software defects. So some of you may have seen this graph before. This is from Barry Bohem's research on software cost estimation from back in the 1980s. So on the x-axis, we have the phases of software development over time, and on the y-axis, we have the relative cost to fix a defect. So if we look at the relative cost to fix a defect, that we create the defect in the requirements phase and we fix the defect in the requirements phase, it will have a relative cost or unit cost of 1. If we find the same defect in the design phase before we fix it, we'll have a relative cost of 5. If this requirements defect makes it to coding, it's a cost of 10. If it makes it to developer testing, it's a cost of 20. And acceptance testing, cost of 50. And if this bug makes it from requirements all the way up to production, the cost to fix the bug is over 150 times what it originally cost if we would have fixed it in production. And several other industry experts have seen the same kind of, or reported the same kind of results as well. This is Steve McConnell, one of Microsoft's software development experts, and Scott Ambler from IBM. So in the waterfall world, we have a set of methods that allow us to find and fix these defects. These methods occur at certain phases of the software development cycle that are relatively high up the curve in terms of the cost to fix them. So we can find defects with reviews and inspections, programming and design defects via traditional system testing, and finding requirements defects through traditional acceptance testing. But as you notice, I mean, these are relatively high up the curve, so the cost to fix them at this point in time is higher. And I'm sure there's other ways that waterfall projects find and fix defects as well too. I think this is just to point out some of the main ones that happen late in the game. In the Agile world, however, we have a series of short-circuit mechanisms designed to catch these defects early in the game when the cost is still relatively low. So on Agile projects, we do stuff like pair programming, continuous integration, and test-driven development, which finds design and programming defects very early on. In addition, we also have active stakeholder participation, so we're finding requirements and design defects as well. We're also finding requirements and design defects with model storming, and defects found by independent parallel testing. And this is in addition to all of the ways you can find them on waterfall projects as well. So the trick here is that if we catch the problem, or if we catch the defects early and we fix them early, we've reduced the cost to fix them quite substantially. And in addition to being able to find and fix defects early, there's also anecdotal evidence that the cost of change curve in Agile is significantly flatter than that of waterfall. And they think that this is because Agile practices like continuous integration, continuous refactoring, and test-driven development make the software significantly more flexible and adaptable to change. In addition, we do things like individuals and interactions, which has a lower overhead cost than using processes and tools as well. And doing things like not having comprehensive documentation means that we're traveling light in the Agile world. We don't have to update a bunch of documents in order to get the artifacts to reflect a change. Essentially, in Agile, we're traveling light. So all of this ultimately leads to Agile having higher adaptability over time compared to waterfall. So on the x-axis, we have time, and on the y-axis, we have the project's ability to respond to change. In the waterfall world, we make these decisions early on, and we're committed to them. And to change them requires quite a bit of rework and to update all of the documentation as well. In the Agile world, however, we're traveling light, so we're staying pretty flexible and able to respond to change quite a bit. Okay, and the fifth idea is self-organization. All All right, we're going to do a quick economics thought experiment for those of you that have not taken an economics class, which I'm guessing is probably very few people given the number of hands I saw. Okay, so the economics guys don't, and gals, you don't get to answer this question because you already know the answer. So imagine for me, if you will, that you're a baker, and your job is to set the prices for baked goods, all the baked goods in the store. So the question is, how do you determine how much to charge for a loaf of bread? Does anyone have any ideas? Just throw something out. Dartboard. That's probably right. Okay, well, there's really no right or wrong answer. The point of the thought experiment is to get people to realize that it's not a trivial thing to do. Setting prices isn't just something you just magically throw a dart and you get the right price. In addition, it depends upon what type of economy you're operating in as well, too, like how you set the cost. And most people have never even given this even a second thought, other than people that have taken economics classes or people that work in bakeries that actually have to set the price. So, from World War II on through the 1990s, with the fall of the Berlin Wall, the world was fighting this Cold War over two opposing social ideologies. And at the same time this Cold War of social ideals was going on, there was also a battle raging between two different types of economies. Half of the world was fighting for command economies, and the other half of the world was fighting for market economies. When you're determining the price to charge for a loaf of bread, if you're in a command economy, you have controlled production and controlled prices. So you've got a central planning agency that's trying to determine how much to set the price, production level and the price for bread. So with controlled production, if we set the production level too high, we're going to end up with surplus and bread's going to go to waste. And if we set it too low, we're going to end up with shortfall. There won't be enough bread to go around. So we also have controlled prices. If we set the price too high, no one's going to buy the bread. And if we set the price too low, we could sell it at a deficit relative to our production costs. And not only do we have to do this for bread, but we also have to do it for milk, cheese, automobiles, essentially all of these different things in the marketplace. So there's millions of price and production level decisions that need to be made, and they need to be made by the central planning agency. So in order to maximize the social welfare for all parties involved, that is to give both the bread consumers and the bread producers the highest value possible relative for what they're each doing, we want to have these price points converge at what's called the competitive market equilibrium, this little sweet spot here in the center. And so by setting the production levels and price using a central planning agency, empirically this is not been found to not be very good at converging to these competitive market equilibriums. It creates what's referred to as market inefficiencies. So either the prices are set too high, too low, or the production levels are set too high or too low. And then the market inefficiencies then accumulate over all of the different prices and production levels that we set in the economy. And to make things even worse, the price of the bread and the production level of the bread also have effects on all of the other goods in the economy, substitute goods and competitive goods, that will also influence the price you want to set the bread at and the production levels as well. So this gets extremely complicated really fast. And some economists have referred to it as a controlled failure consumption. So in a market economy, however, we have millions of entities in the market, and they're all individuals and interactions happening here, rather than a central planning agency. So we have consumers that are willing to pay a certain price, like $1.25 for a loaf of bread, and we have producers that are willing to produce bread for a certain price, say as low as 75 cents, which is the cost of production. So in an ideal competitive market, there's a tension that exists between the bread producers and the bread consumers. And this tension between the two essentially helps the market converge to the competitive market equilibrium in a way that maximizes social welfare for all of the parties involved. So in the market, the forces of supply and demand, rather than a central planning agency, are making these millions of price and production level decisions. And it's based upon billions of transactions, or trillions of transactions that are occurring in the market each day. So some of the prices will be too high, and they'll eventually get set lower over time, and some of the production levels will be too high or too low. And eventually this all kind of converges to the competitive market equilibrium over time. And this way of setting prices and production levels, letting the market figure this out, has been proven to be extremely efficient, provided that you've got ideal markets. And in the real world, we don't have ideal markets. There's all sorts of things modifying efficiency. And some economists have even referred to this as chaotic success. It just doesn't look like it should work. I mean, where's the control mechanism on these millions of interactions between people? So, but for whatever reason, it's actually quite successful. So to understand why this is, we have to look at the field of complex adaptive systems. So complex adaptive systems is a big and scary term, but we're going to simplify it and make it easy to understand. So first we have a system, which is a collection of interconnected things, like this school of fish over here. They're interconnected with one another by their position relative to one another in the water. And they're complex but complex in the mathematical sense, meaning that they're a dynamic network of interactions. Each of these fish are communicating with one another in terms of their position, velocity, and direction that they're traveling. And they're adaptive, which means that they're changing in response to their environment. And they do this to increase survivability. So, for example, we've got this school of fish, and it can swim around in unison, which is through this set of interactions. And by swimming in unison, they look like one giant mass to predators like sharks that are swimming around. So oftentimes it will either scare the shark away or confuse the shark, and thus the survivability of this group as a whole is better than any individual fish swimming by itself. And here's a diagram that might help to clarify some of this complex adaptive system stuff. So we've got these nodes here, which represent the fish, and we've got these lines which represent the interactions between each of the fish. We've got these positive feedback signals coming in that are amplifying some of these, and we've got negative feedback signals which are dampening some of these interactions. So by this simple self-organizing set of local relationships here, we have what's called in the generative sciences an emergent property. And the emergent property is the complex adaptive behavior of the complex adaptive system itself. So essentially, the behavior of the school of fish is a property that only exists when we have a collection of fish interacting in this complex adaptive system called a school of fish. Essentially, the whole is greater than the sum of parts. And complex adaptive systems are fundamentally different from traditional systems of control because they have inverted control structures. So most control structures we're used to are these top-down command and control style structures that we typically refer to as bureaucracies. Whereas complex adaptive systems are bottom-up and self-organizing, and they can self-organize to be more efficient and adaptable in certain situations. They refer to these now as adhocracies. It's kind of a fancy term. I actually had to look it up to see what it meant too. So one of the advantages of these bottom-up self-organizing adhocracies is a phenomenon referred to as the wisdom of the crowds. So the wisdom of the crowds is an idea in psychology that if you take the collective guesses of a bunch of people, oftentimes the answers will be better than experts in aggregate. This works really well for certain categories of reasoning, things like quantity estimation, general knowledge, and spatial reasoning. It doesn't work very well for other things like domain expertise or domain-specific knowledge. The domain experts typically dominate this category. And it's important to note that not all crowds are wise. Two crowds I can think of that are not wise, stock markets in a panic, and large groups of people with a lot of alcohol involved, especially if their favorite sports team is lost, or one for them. Interestingly, this phenomenon also exists with machines. So essentially machines exhibit the same aggregated behavior, or the same behaviors in aggregate. Fortunately, though, the machines we're talking about are not these kind of machines here, but the kind of machines that I was working with at Iowa State when I was studying machine learning there. So in machine learning, which is a subfield of artificial intelligence that uses computers and statistics in order to simulate rational decision-making processes, we have a specific category of machine learning algorithm called an ensemble learner. And with an ensemble learner, rather than creating a single super smart machine learning algorithm, we instead create a bunch of weak learners, or kind of average Joe machine learning algorithms. And so if these average Joe algorithms produce better than random guesses in aggregate, produce better than random guesses on average, we can essentially aggregate their responses and get a better answer from the set of them as a whole rather than the individual decision trees. So if we combine all of these decision trees, we end up with something called a random forest classifier. And this is a project I worked on where we were trying to do human activity recognition using the accelerometer and the gyroscope of your smartphone. So I was trying to determine whether you were sitting, standing, walking, running upstairs, whatever you were doing. And so, as you can see here on the x-axis, we have the number of decision trees involved in the random forest classifier. And on the y-axis, we have the error rate. So even with, and these color lines here, these are essentially the error rates of the individual categories of classification, like sitting, standing, walking. And as you can see, even by adding just a few of these decision trees to the process, the error rates drop pretty dramatically and pretty fast. So by the time we get to about 100 decision trees, the random forest classifier is essentially maxed out its decision-making predictability capabilities. So how does this apply to Agile teams? Well, first, Agile teams are self-organizing versus command and control structures. So this allows them to reorganize to complete tasks in ways that are more efficient, adaptable than command and control structures. In addition, Agile teams have inverted control structures as well. So information and direction regarding certain aspects of the projects come from the individuals and interactions within the team rather than from top-down policies and procedures. And this allows Agile teams to operate as complex adaptive systems, continuously adapting to changes in the requirements of the project and to operate more efficiently overall than traditional top-down command and control style teams. And finally, Agile teams exhibit this wisdom of the crowd phenomenon as well. They make better decisions in aggregate often than, or more often than individual decision makers in, once again, specific categories. For example, planning culture, which is an XP practice for software estimation, has been empirically proven to be more effective than other methods of software estimation involving individuals trying to make estimates. And the sixth idea I'd like to talk about is efficient communication. Okay. The cost of poor communication is enormous, but it's really hard to quantify, and it's a hidden cost as well. It's not on the profit and loss statement, so you can't just, as a manager, look at the P&L and be like, oh, we lost a whole bunch of money for miscommunication this year. We need to do something about that. But the expense is still real. How many of you guys got it? 100%. So, despite the fact that this is really tough to quantify the cost of miscommunication, there have been some attempts to do so. So in 2009, SIS Marketing Research did a study where they're trying to quantify this for large enterprises with over 100 employees. So what they found is that they estimated that 17.5 hours per knowledge worker per week was lost due to miscommunication. Some of the top issues they encountered were waiting for information, unwanted communication, or the noise that happens, inefficient coordination amongst team members, barriers to collaboration, and customer complaints. And if you look at this visually and stack this up, I mean, this is a huge amount of time. This is like half of a knowledge worker's week that was lost due to inefficient or poor communication. In fact, they estimated the total annual cost of poor communication per enterprise knowledge worker to be over $50,000. That's just enormous. So let's take a look at some of the aspects that influence the effectiveness of communication. First, we'll take a look at communication structures. So in an area of mathematics referred to as graph theory or network theory, we model communication as complete graphs. So we've got these nodes here, which represent the people, and we've got these edges, which represent the communication channels between the people. Now, as you increase the number of nodes, the number of edges or communication channels increases quadratically in the number of the nodes that you have. That's order n squared for the programmers in the room. So I had to give a shout out to my programmers. It becomes extremely inefficient very fast. So, in a nutshell, with communication structures, you have to keep your team sizes small. Otherwise, you'll overload the communication structure with inefficiencies. In addition, if you've got a project that requires significantly more than 7 plus or minus 2 people or so, a more efficient communication structure is something referred to as a sparse network. And so a sparse network essentially has these highly cohesive units, but is also loosely coupled as a whole. So you've got essentially like component teams working on also highly cohesive and loosely coupled pieces of software. An interesting side note, they found that the optimal interconnection densities, the way these interconnect, follow the 80-20 rule. So it's just blew your mind. 80-20 rules all over. And now let's take a look at some different modes of communication and their relative effectiveness, richness and effectiveness. So we've got the richness of communication here on the bottom, and we've got the relative effectiveness of communication here. So we've got paper down here at the bottom, which is your traditional documentation. And as we move up, we end up with more rich and more effective communication, audio tape, but I don't know anyone using audio for software documentation. We've also got videotape up here. And then for our modeling or our collaboration options, starting here with email conversations, moving up to phone conversations, video conversations, face-to-face conversations, and then the most rich and also the most effective is face-to-face conversations at a whiteboard. And to understand why there's such a strong correlation between the richness of the communication and the effectiveness of the communication, we need to look at a field called information. So, in a subfield of information theory referred to as signal theory, we have a concept called signal-to-noise ratio. And signal-to-noise ratio is when you take the power of the signal and you divide it by the power of the noise. So the signal is essentially everything you're trying to communicate, and the noise is everything else around that's interfering with the signal. And so the goal in signal theory then is to maximize the signal-to-noise ratio, subject to certain constraints. So when we're maximizing signal on a software project, we want the signal is essentially the necessary communication, the stuff that we need to communicate to the team. And so we want to maximize the bandwidth of this signal by doing things like having face-to-face conversations and by using whiteboard. And if we're maximizing this bandwidth, that increases the fidelity of the signal and thus maximizes the likelihood that the message will be received and minimizes the likelihood of miscommunication. We also need to minimize noise too, and with apologies to Motley Crue fans. So noise is the unnecessary communication that happens on the project. And we want to minimize noise by doing things like minimizing the bulk emails that get spammed out to all the developers. In addition to having room layouts that support good agile collaboration as well. We also want to minimize the environmental noise, especially intelligible human speech. The studies on cost of contract switching from like having like salespeople in earshot of the software developers distracting their concentration. The evidence is really strong. I mean, if the software developers don't have quiet working conditions, you're essentially wasting huge amounts of money. And so, why is this important, and what does it have to do with Agile? Well, Agile teams are designed to maximize the richness of their communication and thus minimize the cost of miscommunication. They're small, limited to 7 plus or minus 2 or 6 plus or minus 1 people, depending upon who you talk to, with a preference for smaller teams. So that keeps the communication effort efficient. In addition, they use this concept of the full team, which is we get everybody that's working on that part of the project in the same physical room, and we have them working together as a collection of highly cohesive, generalizing specialists. And in addition, we also use things like face-to-face collaboration to maximize the bandwidth of communication. And we do things like pair programming, which creates an extremely rapid feedback loop between two software developers as they're working together to solve problems with code. We also do things like daily stand-ups, which allows us to get the necessary information out each day to the team and to minimize the number of like status updates meetings that we have to have as well. We also use information radiators in order to radiate out information necessary to the project through things like Scrum boards. And this keeps our communication more transparent as well. So another thing I would like to talk about is how documentation is different on Agile versus Waterfall projects. So in the Waterfall world, the documentation is the blueprint and the code is the product. So documentation is acting as a blueprint for the product that you're building, which is the code you produce. But as we all can attest, documentation is typically out of date, it's rarely ever read, and it's not executable. We can't run a test and ensure that the code is doing what the documentation says it's doing. In Agile, however, they look at the code as the blueprint and the executable software as the product. So we've got code, which is acting as a blueprint for our product that we're creating, which is the executable software running on the end user's machine. The thing is, code is always up to date. You can press the compile button on the IDE, and you're always going to get the code, you're going to get the executable with the latest source code. It's also continuously read as well, because the developers are in there working every day. And it's an executable specification. So we can take our unit tests, our integration tests, and our VDD tests if we're doing behavior-driven design, and we can use these specifications to verify that the software is doing what it says it's supposed to be doing, in addition to running them automatically and essentially making self-verifying blueprints on the product. I think that's a very powerful concept when you use test-driven development and VDD as well. There's also quite a bit more visibility on Agile projects than Waterfall. So on the x-axis we have time, and on the y-axis we have visibility of the project. So in Waterfall projects, they often start with a high degree of visibility where everybody is communicating and collaborating early on in the project. And then after the kickoff meeting, everybody kind of runs off into their corners to work on their individual components. And then we start integrating them later on in the meeting. And as we're integrating them, the visibility returns up until the point where we're sitting in a project review meeting and we're either celebrating the success of the project or promoting the failure, possibly looking for a new job. Agile, however, keeps everything on the surface. So by using our information radiators and by having regular inspection and adaptation, the sprint retrospectives that we're doing every 2 to 4 weeks, depending upon the length of our sprint, we're keeping all of the problems on the surface and talking about them. In addition, and this is the most important, having frequent delivery of working software means that problems have no place to hide. Essentially, if you're creating potentially shippable software every 2 to 4 weeks, any problems you run into have to be solved in very short time frames. The inventory that the waterfall process has with it just allows problems to hide. So essentially, by staying on the surface, problems have nowhere to hide in the Agile world. And one last topic I'd like to talk about regarding communications and metrics, or the way we communicate how well a project's going or how poorly it's going for that matter. Most of the metrics that are used on Waterfall were derived from traditional cost accounting, which was originally designed to manage workers and machines in assembly line processes. So the goal of cost accounting is the goal of cost accounting is cost reduction, and it looks at labor as a variable cost. So it makes the assumption that labor is interchangeable. But we know in the software world we can't just double the number of developers and get twice as much code out. Unlike like an assembly line where you could just double the number of workers and double the number of the machines, and pretty invariably you'll get double the amount of widgets out of it. but we're not producing widgets, we're producing code. So this, in a nutshell, it just doesn't work well as well for software development. In addition, metrics have consequences. So in science, there's this phenomenon referred to as the observer effect, which means that in certain systems, when you're making a measurement of the system, by virtue of measuring it, you're actually influencing the phenomenon being measured, and thus changing it. In psychology, they see the same thing. In observational studies, when people know that they're being observed, they behave differently because they know they're being observed, so it just changes the way they interact. And it's not magic, there's real interactions, like you're actually influencing the thing that's going on. So in project metrics, of software projects, gathering these metrics is also interfering with the process. And in worst cases, it's actually causing the people being observed to start gaming the system. Their behavior changes in ways that make the metrics look like they're favorable to them. And then once you've got metrics that are skewed because of these things, they're essentially not worth collecting because they're not telling you what you need to know. In addition, gathering metrics has a cost. There's both the direct cost of the time and the software that you use to gather the metrics, and indirect costs, things like the interference with the process, and the fact that people start using metrics to play the blame game and the reduced morale from that. Essentially, most metrics don't really provide a whole lot of benefit in Agile projects, at least not that I've seen. And I'm a big data guy. Like I built my whole career around analyzing data. So Agile has these, what I consider at least to be better ways to gain this similar knowledge. Things like retrospectives, simply asking the developers and having the developers talk about what are the problems. Are we seeing more bugs or what's going on here? It seems to work better when you have small team targets. But if you do have to measure something on a team, I think the two things that are most important are working software. This is our measure of success. Are we continuing to release working software? And time to feedback. How long does it take for us to get feedback from something we need to know? Like when I've done something, was this the right thing to have done? And the last topic we're going to talk about is feedback. I think we're running real short on time.
Like maybe 5 minutes.
10 or 15 minutes? Okay. I'll do my best to, I can get everything. Okay. So imagine for me, if you will, you're in a hotel room and you've got this shower now in front of you and you're trying to figure it out. You turn it all the way, wait 30 seconds and the water's freezing cold. You turn it all the way the other way and it's like scalding hot. Wait another 30 seconds and it's freezing cold again. And you keep oscillating back and forth until you find this perfect little sweet spot here where the temperature's just right. So in systems like this, having a rapid time to feedback is really important because we need to have rapid feedback in order to learn the system, in order to interact with it and manipulate it. Time to feedback is also important on software projects as well because of this idea referred to as the cone of uncertainty. So on the x-axis we have time, and on the y-axis we have the estimate variability. And the empirical research that led to this cone of uncertainty showed that about at the beginning of a project, when we have a whole lot of unknowns and we're not really sure how everything's going to go, our estimates are typically off by a factor of 4. And then this diminishes over time as we learn and we reduce our uncertainty. It reduces asymptotically as it approaches 0 here. And then at the end of the project, the uncertainty is essentially 0. We know as much as we're going to know about the project. So in order to reduce uncertainty on a project, we need to learn over time. And learning requires feedback. In fact, in looking at educational studies, when looking at the effect size of learning, effect size in learning, the single most important variable in students' learning is feedback. And so we need to have this continuous and rapid feedback loop in order to allow us to learn more rapidly and reduce our risk. So in the Agile world, we have a lot of multiple levels and timescales of feedback going on. So at the bottom here, we've got feedback in the order of seconds with pair programming, unit testing in the order of minutes, pair negotiation in the order of hours, stand-up meetings daily, acceptance tests on the order of days, integration plans weekly, and release plans of the month, in addition to other things like continuous integration and test-driven development. And this allows us to learn quite rapidly. In addition, some Agile practices, primarily in the lean startup movement, recognize this idea of smart failure. So with smart failure, we're doing a bunch of really small, frequent experiments, and we're going to end up with a lot of small failures and a lot of small successes. And the idea is that these experiments have a relatively low cost to execute, and they give us high value because of what we're learning and what we're reducing in terms of concern, like these cookie monsters. In the old world, we had time to sit back, think, and make decisions with our data. In the new world, however, we don't have time to do that. So we have to run these little experiments in order to, to learn faster and to adapt. And this requires a mindset change. It is quite a big mindset change because in the old world, if someone made a decision and it was incorrect, they would discipline them or whatever. In the new world, however, if you've got a guy that has an idea, he runs an experiment, finds out that his idea was wrong. I mean, you shouldn't discipline the guy. nice, buy the guy a pizza. I mean, he learned something. He eliminated some risk of the project and learned something you didn't know. His idea was a good idea. So the mindset changes is that it's okay to fail small and it's okay to fail smart. However, it's never okay to fail big. And the way we minimize these epic failures is by having these small experiments, running these experiments, and doing continuous feedback. Another way that Agile utilizes feedback and learning is by delaying critical decisions to what's referred to as the last responsible moment. So over time on a project, our knowledge increases, which means the risk of creating an error is decreasing. And so we want to do as much learning as we can before we have to make critical decisions, and then make that decision when we have more information available. This essentially reduces the risk of making an error, and it may seem counterintuitive, the idea of, well, if we're delaying these critical decisions, how is that reducing our risk? But when applied correctly, it's actually a pretty solid risk mitigation strategy. And one of the best ways I've learned recently to reduce uncertainty and risk on novel software projects or projects with a high degree of market uncertainty is this idea from the lean startup movement called minimum viable product. And this is the idea that there's primary features and there's secondary features. Primary features being what the users need, and secondary features being the things that the users want, but they don't actually need to solve the business problem. So with the minimum viable product, we solve the core use case first. We then release this minimal feature set software, get it out in the market right away, start gathering feedback, and thus validating your assumptions. So metaphorically, imagine you've got this grand idea for something you call the donut. And you want a minimum viable product to see if this is worth pursuing. So you don't build this donut down here with all the sprinkles and glaze. You build the simplest possible thing you could. You get it out there in the market to people that are friendly to the idea of using a minimum viable product. And then you find out, do they actually like the donut? Because if you find out they don't want a donut, they instead want a bagel, you don't want to waste your time building sprinkles and glaze and chocolate and all this stuff. When in fact you should be working on cream cheese next, because you put cream cheese on a bagel. So the main benefit of this feedback that we receive from interacting with our MVP is that it allows us to pivot or change direction when our assumptions prove to be incorrect. And we want to pivot earlier versus later because this minimizes the cost of pivot. In addition, by pivoting as early as possible, we're reducing the likelihood of falling into this trap called, or a bias that every one of us has, called the sunk cost fallacy. So in economics, a sunk cost is a previously incurred cost that cannot be recovered. So rational decision making requires that we don't look at our past losses. We only look at, consider our future returns on something. I had a metaphor to tell, but for time's sake, I think I'm going to move on. Human beings just have this predictably irrational bias about them. And so the way we avoid this fallacy is by taking small incremental steps, releasing incremental software, gathering feedback, and pivoting as early as possible. And this means that we're staying minimally invested. So the further we get invested, the harder it is for us to get out of it. And you poker players know what I'm talking about. So all this feedback, learning, smart failure, etc., combined in a way that significantly reduces our risk on an Agile project over time. On the x-axis, we have time, and on the y-axis, we have risk of the project. Waterfall reduces risk relatively late when we're doing the integration and when we're finding out whether we built the right software for the users or not. Whereas the Agile software, we release it early, we're getting feedback, and we're reducing our risk early on and over the life of the project. So one final benefit that this continuous and rapid feedback on Agile projects provides is that it allows us to know when to stop. So on the x-axis, we have the time, cost, or effort, and on the y-axis, the marginal return on investment of each feature. If we're building our features in terms of highest priority features and working our way down, the value that we're getting from each feature, the return on investment is decreasing over time. And at some point, essentially, the cost of a feature is equal to the value we're getting, where our ROI is 0. And then any features beyond that, the cost to create the feature is actually less than the value we're getting from the feature. And we have a negative ROI here. So if we look at the cumulative return on investment of the project as a whole, essentially we have a curve like this because it's accumulating over time. And this is the point where we want to stop, the point where we're no longer getting as much value out of the feature that we're creating than the cost to create the feature. And this is also good for presentations, not just Agile software, because this is everything I wanted to cover, in addition to everything we already covered, but due to time constraints and attention spans, I just have to stop. So essentially, I just created a mini project backlog, looked at it like a little Agile project. I had a product backlog, all the ideas I wanted to cover, and then I just worked on them one at a time until I ran out of scope, or I ran out of time. And essentially, this is where we're at. So with that, I'll stop the presentation. Hammer time. So in conclusion, why is Agile so successful? It's well adapted to the world after midnight. It inverts the project management constraints. It prioritizes features by business value. It embraces change versus following the plan. It utilizes the efficiencies of self-organization. It creates efficient communication, and it provides continuous and rapid feedback. And speaking of feedback, feedback's very valuable to me. So if you guys have any feedback on things that you liked or could have done better, I'd love to hear them. And here's my contact information if you'd like to learn more about me or send me some feedback. Awesome. Thank you very much.